Alright class, this is 3.4. We're going to talk about velocity and other rates of change. First of all, just to note, we're going to write this definition down again because it's been a while. Rate of change. So instantaneous rate of change is the rate of change of f with respect to a. So this is at a point. So it's given as the limit as h goes to 0. And by the way, this is f prime of a, we would call it. Again, this is at a point. F of a plus h minus f of a all over h. If it was the function, it would be f of x plus h minus f of x. But this is at a point. Alright, so let's find the rate of change of the area with respect to its radius. Well, first off, we need to find the equation of a circle, area of a circle, which is a equals pi r squared. So since r is the variable there, remember pi is not a variable, it is a number. It's like saying I have 3r squared. You do not have to do product rule here. So I'm going to find the rate of change by taking the derivative. So I would say dA over dr is equal to 2 pi r. You don't need an r prime or anything because we took it with respect to r. So that is the equation. So then part B just says evaluate that equation when r is 5. And when r is 5, we get that the area is changing at a rate of 10 pi. And we'll talk about the units in a second. When r is 10, you get 2 times pi times 10, or that it's changing at 20 pi. And so if r is measured in inches and a is measured in square inches, what would the units be for dA dr? Well, think about what's on top. The area is on top, so it would be inches or square inches of area per inch of radius. Which means that if we look back at B, we can say that when r is 5, the area is changing by 10 pi square inches for every change in inch of radius. That's how we would say that. Alright, what displacement is. This one gets people. Displacement is not where you are, it's how you have moved. So, how far something has moved from one time to another. Okay. We would usually say it's the change in position. So change in s, we're going to use s as position. Now, average velocity is the change in position over time. How far did it move and how long did it take to do that? We've been doing that already. So V average is equal to displacement over time, or travel time we'll call it, which is equal to change in s over change in t. Now, that is just finding the position at 2 points and doing like a slope equation or rate of change equation. Instantaneous velocity, though, again, instant means you're taking the derivative of position. And this will give you the speed at a point. It's not an average. So we would call that v of t is the derivative of position s with respect to t. And speed is the absolute value, because speed, remember, doesn't have a direction. So if your velocity is negative 10 miles per hour, you're really going 10 miles per hour just in the backwards direction. So speed is the absolute value of velocity, because you wouldn't say you're going negative 10 miles per hour for speed. That doesn't make sense. The negative for anything like that just deals with the direction with velocity. So it's the absolute value of the velocity. Good. All right. Let's go on. This you have to be very careful about. This is a velocity versus time graph. It's 4 by 36, so this is going at intervals of 4. And time goes up by, I think, ones. Yeah. So this student's walking in front of it, and it's recording the speed, or I guess velocity, I should say, which is direction. So again, when you're looking at these, we're not looking at the slopes of these curves. We're just looking at the curve itself. From here to here, the velocity curve is above y equals 0. So velocity is 0. So that means that she is moving forward during those first 14 seconds. So we would say from 0 to 14, students moving forward. Now, during 4 through 8, she's moving the fastest forward and then starts slowing down because that's when her speed is a max. The next 12 seconds, so from here to here, so from 14 to 26, that's 12 seconds, the student is moving backwards. Then, from t equals 26 up to 32, notice how the velocity is 0. It's on the line velocity equals 0. So the student is standing still. And that's the only time that she's really standing still. These other places where velocity is 0 is just an instant. It's change of direction. Alright, so we have that. And then moves forward again. When t is greater than 32, moves forward. Now it says, when is her speed a maximum? Remember, speed does not matter about which way you are going. So really I'm looking on this chart and figuring out where the highest or lowest point on the curve is. And if you guys notice, it should be at about 20 seconds. It looks like it's at -7, which means the speed's 7. Whatever the units are here, feet per second or meters per second, probably feet per second. So speed is a max at t equals 20 seconds. Okay? And again, she's moving backwards, but it doesn't matter. I want to know how fast she's moving. She's moving the fastest there. Okay, now, this kind of goes with this. Acceleration is now the derivative of velocity. So if you guys remember, so if we look at this velocity curve and we look at the slopes, that would tell us acceleration. So for example, back up here, from 4 to 8, she's not accelerating or decelerating, or I guess accelerating in the negative direction at all. She's moving at a constant speed of 4 whatever units per second. So anyway, so acceleration is the derivative of velocity. With respect to t, or with respect to time. It would help if I spelled time right. Alright, time. So the notation for this is a of t is equal to the derivative of v of with respect to t, or it's also equal to the second derivative of position. We learned this back in parametrics, free fall motion. In free fall motion, position is given by 1/2 at squared, which is equal to an acceleration due to gravity. So I should actually call this g, where g is equal to 32 feet per second, or 9.8 meters per second squared. Sorry, it's an acceleration. Alright, so anyway, that means that we can come up with position curves on Earth that tell us, and sometimes it'll be negative depending on which way you want to orient gravity. And that's why in a lot of our quadratic equations we get 16t squared when we are modeling things on Earth, because it follows that curve, or s can equal 1/2 9.8. But again, a lot of times we'll put a negative on or attached to it so we can talk about that it's moving in the down direction is negative. Alright, let's look at this equation. A dynamite blast propels a heavy rocket straight up with a launch velocity of 160 feet per second. It reaches a height after t seconds following this equation. Okay? How high does the rock go? Now, whenever you see a maximum height, think about what's happening. The rock is going upward, 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 and then it hits its highest point. What's happening at the highest point? The rock has momentarily stopped because it's going to start coming the other direction. Okay? So whenever you get how high does the rock go, or the top or the max height, you have to think that the velocity, we want to know when the velocity is equal to 0. So in order to do that, we need a velocity curve. And I'm going to do part A and B on this sheet and then go down to the other sheet. So velocity is equal to 160 minus 32t. So that's my velocity. And I set that equal to 0. And I get that it's when t is equal to 5 seconds is when the velocity is 0. Now, next thing I'm going to do is plug that back into my position. I want to know what is the position of the rock at 5 seconds. So you get 160 times 5 minus 16 times 5 squared. And you get that the highest the rock goes, which is at 5, is at 400 feet. Okay? So now it says what is the velocity and speed of the rock when it is 256 feet above the ground on the way up and down. So in this equation I'm giving you a position. So I need for part B to use my position equation to find the time. So I know that my position is 256, and that's equal to my position equation. I have a quadratic here, 16t squared minus 160t plus 256 equals 0. You can divide everything by 16, so you get t squared minus 10t plus 16 equals 0. You can factor this, two numbers, 8 and 2. T minus 8 and t minus 2. So that means that we want t equals 2 seconds, t equals 8. And then, without even looking at a graphing calculator, by the way, you can use a graphing calculator for all this, but it's faster not to bring that up. You should know just inherently that at t equals 2 seconds, it's going up, and then on t equals 8, it's coming back down, just by laws of nature. So what is the velocity and speed when it's 256? So basically now I need to do my velocity at 2 seconds, which is 160 minus 32 times 2. And I get a velocity of 96 feet per second, which means it's moving in the upward direction. My speed is also that, because speed is just the absolute value of v, which is still positive 96 feet per second. But at 8, on its way down, we get negative 96 feet per second for the velocity. But again, we would say, well, it's still moving at a speed of 96 feet per second. It's just moving that way in the downward direction. That's why it's negative. So, what's the acceleration of the rock at any time? So that's basically saying take the derivative of velocity. So for part C, the derivative of velocity is just, it's negative 16t, so negative 16. And then from there, well, that's not true, actually. It's negative 16t squared. I'm looking at the wrong equation. Velocity's right here. So, derivative of that is just negative 32, which makes sense. So acceleration at any time is equal to the derivative of velocity, which is equal to negative 32 feet per second squared, which makes sense because that is the actual acceleration due to gravity, and that's not changing at any time along that curve. And then part D says, when does the rock hit the ground? Well, that's when my position s equals 0. So I'm going to say 0 equals 160t minus 16t squared. When you have something like this with no third number, you factor out a GCF. I get 16t times 10 minus t. And you get equals 0. And you get t is equal to 0 or t is equal to 10. Now, that makes sense. However, t equals 0 is when it leaves. So I want to look at this. When does it hit the ground? T equals 10 seconds. So it hits ground. T equals 10 seconds. Which makes sense. If it leaves at 0, ends at 10, we found earlier that our maximum height was at 5, which is halfway in between that curve. Alright, so this problem is probably more important to know. They're all very important though. Displacement, again, means how did it move during the first 2 seconds for this particle that is modeled by t squared minus 4t plus 3 anytime starting at t equals 0. So in order to know how it moved, we first have to find out its starting point. It didn't start at 0. When you put a 0 into the equation, you get 3. Now we're going to do 2 seconds. So 2 squared is 4 minus 8 is negative 4 plus 3 is negative 1. So at 0 it's at 3, at 2 it's at negative 1. So our displacement is the change. And that's equal to negative 1 minus 3, or negative 4 meters. Which means it moved 4 meters in the negative direction, whichever direction that is. Right? Let's say it's right. Or I'm sorry, left. Usually right is positive, left is negative. Alright, average velocity. Average means we're just doing the slope. We already have it's displacement over time. We know that during it's during the first 4 seconds, so it's a little bit different from part A. So for part B, we need to know what S of 4 is. We need to know where it is after 4 seconds. So that's 4 squared minus 4 times 2. Nope, it's 4 times 4 plus 3. And if you look at this, it's at 3 again. So, think about this. The average velocity from 4 to 0 is just 3 minus 3 over the change in time, which is 4 minus 0, which is 0. And that is, again, meters per second. So it has moved 0 meters. The average was 0 because it ended up at t equals 4 at the same place it started at. That doesn't mean it didn't move during those first 4 seconds. It just means the average is that. Find the instantaneous. So that would be when t equals 4. Instantaneous is the derivative. So I'm going to go back up here and take the derivative. So velocity with respect to t is equal to 2t minus 4. And then it says at t equals 4, v of 4 is equal to 2 times 4 minus 4, which is equal to 4 meters per second. So even though the average from 0 to 4 is 0, at 4 seconds it's moving at 4 meters per second. So what's part D? Find the acceleration. So I'm going to take the equation 2t minus 4 and take the derivative of that, and I get the acceleration is equal to 2 with no t. So that means at any time the acceleration is 2 meters per second squared. And finally, describe the motion, and at what you can look at the graph for this. So you want to look at your graph, and you can look at any graph you want. Position, velocity, or acceleration. It's probably easier to look either at velocity or position. So from 0 to 2, particles moving backwards. It starts at a position 3 meters and then goes to -1 meters during that time. So at t equals 2, the particle stops and changes direction. And then after that, when t is greater than 2, it moves forward and accelerates. Well, it just moves forward, I should say, for the rest of the time. Okay, so that's that. All right, economics. Real quick, I'm going to just do these quickly. So in economics, just another way to show how we can use derivatives. Rates of change are called marginals. So normally there's a cost associated with producing something. We're going to call that C of X, cost of producing X amount of units. So that's saying I'm producing, 100 thingamabobs, I don't know, Snuggies, or I don't know what else, glasses, whatever, anything you could think of. The marginal cost then of production is equal to the change in that cost with respect to the number of units. And you can do the same with revenue. Remember, revenue is the money you take in. Cost is how much you are paying to get this all happening. Oh, sorry. This should be revenue. So you can do the same thing with revenue. Okay, so let's look at this. It costs you that many dollars to produce X radiators only when X is 8 to 10. So this is the equation for that, and then the revenue is given as that equation. We are currently producing 10 radiators a day. Find the marginal cost and marginal revenue. So marginal cost equation is equal to 3x squared. I'm just taking the derivative of the cost equation, minus 12x plus 15. And if I want to know the marginal cost of producing one more unit at that stage, when we're at 10, I'm going to plug 10 in. So if I want to produce one more unit, it'll cost me $195. So again, what that means is the marginal cost of producing one more radiator a day, when 10 are already being produced, that's the key, it's not any time, is $195. Okay? Now, if I have a revenue, I want to know the marginal revenue. You take the derivative of the revenue curve, 3x squared, using our power rule, 6x plus 12. And the revenue we would take in by adding one more radiator when we're already producing 10 is going to be $252. Which means that if I increase from 10 to 11, it'll cost us $195, but we will take in $252. So this tells us we should probably do that. Alright, so that is how we can use calculus with economics.